Welcome back to the deep dive. Today, we're doing something a little different. We are shelving the big philosophical debates about, when AGI is going to show up.
Right. No more timelines.
No more timelines. Instead, we're picking up the engineering blueprints. We're moving past the when to the much, much harder question of, well, how? How do we actually engineer a general mind?
And that's really the core of it. This deep dive is all about dissecting let's call them the architectural and the representational challenges that are, frankly, stopping us from building true AGI right now.
I mean, for years, AGI has felt a bit like science fiction, hasn't it? It's this hazy, far-off goal.
Oh, completely. It's defined by these, very hand-weighty descriptions.
Mm.
But the sources we've pulled together for you today, they're different. These are rigorous papers on things like cognitive architectures, universal knowledge models, and brand new ways to, actually evaluate these systems.
So we're getting into the weeds.
We are getting squarely into the pragmatic details. We're looking at the foundational building blocks, the actual design principles, and this is the really critical part, the quantitative metrics, the numbers you need to build, test, and then verify that you have a general intelligence that is, auditable and hopefully safe.
Okay, so our mission today is pretty specific then. We're taking this very diverse and, let's be honest, highly technical stack of sources, and we're synthesizing it. We want to give you, the listener, a really clear, structured view of what this next generation of cognitive architectures looks like.
Right. And to understand what's coming next, you have to understand what we have now and why it's just not enough.
It's not just a matter of scaling up what we have. It's a different kind of thing entirely.
It's a different beast. I mean, the systems we have are amazing, but they are essentially very, very good expert tools. And that distinction is, I think, the only place we can really start this conversation. We absolutely have to draw a bright line between what we mean by AGI and narrow AI, or what we used to call expert systems.
Right. Expert systems. So think of like a system that can diagnose a specific medical condition from a scan better than a doctor.
Exactly. Or, a system that can play one game, chess, Go, whatever, better than any human. They're transformative. They provide these incredible high-quality solutions, but, and this is the but, only within a really narrowly defined context.
So they have incredible depth, but zero breadth.
Zero breath. They cannot, for the life of them, translate that knowledge outside of their one little box. AGI cognitive architectures, on the other hand, aim for what the sources call wide coverage.
Wide coverage.
So the whole point is to solve a diverse set of tasks in completely different, totally unconnected fields. And what's more, the intelligence has to be at the system level. The whole thing has to be intelligent, not just, a bunch of specialized parts cobbled together.
It's about being a generalist, like a Renaissance person, not just a master craftsman in one single trade.
That's the perfect analogy. And, while that sounds really abstract, this isn't just theory anymore. People are actually trying to build these things now.
Okay, so what's the temperature check on the current landscape? What's out there?
Oh, it's very active. The sources we looked at, they analyzed 42 distinct existing cognitive architectures that are explicitly aiming for AGI. So these aren't just, musings on a whiteboard. They are actual research prototypes trying to tackle this huge problem.
42. Okay, so what are some of the ambitions here? What are they trying to do?
Their goals are, they're fascinatingly ambitious and often really interdisciplinary. So, for instance, you have the SOAR architecture. Its stated goal is to combine deep insights from psychology, neuroscience, and traditional AI to build a unified theory of intelligence.
So right from the start, they're admitting this isn't just a computer science problem. They're trying to basically reverse engineer a mind.
They are. And then you have another one called Sigma, which is engineered with a very specific and very human goal in mind to naturally support theory of mind.
Theory of mind. So the ability to understand that other people or other agents have their own thoughts, their own beliefs, their own intentions that might be different from my own.
That's it. It's a critical, uniquely human thing. And a truly general agent has to be able to navigate a world that's full of other minds with competing goals. It's not optional.
And what's the most audacious goal you saw? The moonshot.
That would have to be the Hakonen cognitive architecture.
Yeah.
Its goal is, and I'm not making this up, to achieve nothing less than machine consciousness.
Wow. Okay.
Yeah. This is the attempt to build a system that doesn't just process information, but, understands what it's doing and why it's doing it. A system that could, in theory, self-reflect. So, these existing attempts are setting an incredibly high bar for what the next generation needs to even think about, especially when it comes to self-awareness and social modeling.
Okay, so let's unpack that. Let's get into this core philosophical shift that's driving the need for these new blueprints. We have these incredibly successful AI systems right now, especially, the big deep learning models. But the sources we read are crystal clear. They say these systems suffer from fundamental architectural flaws.
That's right. Flaws that structurally prevent them from ever scaling up to true generality.
Yeah.
It's not just a matter of more data or faster chips.
So what is that core limitation? What's wrong with what the sources call experience-driven AI?
The central critique is, I think, really powerful and kind of unavoidable. Current systems, especially deep learning, are basically what the sources call architects of experience.
Architects of experience.
They're master statisticians. I mean, they excel at pattern matching, at finding these incredibly subtle correlations inside massive, massive data sets. But, and this is the fatal flaw, they critically lack an internal, manipulatable causal world model.
Ah, the causality gap.
The causality gap. They can associate A with B a billion times and get really good at predicting B when they see A, but they can't represent the abstract logical chain that actually links A to B. They know what happens, but they have absolutely no idea why it happens.
Or what would happen if you tweaked the system in some new way it's never seen before?
Exactly. And because they don't get causality, their knowledge is fundamentally opaque. It's fragile. Think about adversarial examples. It's a perfect illustration of this.
Right, where you can add a tiny bit of digital noise to an image of a stop sign, something a human wouldn't even notice.
And the model suddenly misclassifies it as a refrigerator
Bigger.
or a banana. It's completely catastrophic. And you have to ask why. It's because the model never learned the concept of a stop sign. The red octagon that signifies a legal command to stop a vehicle. It just learned a complex statistical surface of pixels.
Which is terrifying if you're thinking about putting these things in self-driving cars.
Terrifying. And it points to the other big problem. You can't audit them. Their knowledge is this one big, non-modular, opaque blob. If you find a flaw, say, the system has learned some kind of awful bias from the data.
You can't just go in and find the bias.dll file and delete it.
You can't. There's no line of code to fix. To change one tiny factual association, you might have to retrain the entire system, billions of parameters, from scratch. That is the complete antithesis of general intelligence, which should let you make surgical updates to your knowledge.
Okay, that makes total sense for deep learning. But what about the older approaches? Before deep learning, we had decades of classical symbolic cognitive architectures, things like ACTR, that used explicit rules and structured knowledge. Shouldn't they have solved this?
You'd think so. And they did solve the auditability problem for sure. But they ran into an equally critical, though totally different problem. The value grounding problem.
The value grounding problem.
So in an architecture like ACTR, a system makes a decision by picking an action based on the, quote, learned utility of its production rules, which really just means, which rule worked best in the past in a similar situation.
So if I'm trying to open a door and I have 10 different rules for how to do it, I'll just pick the rule that has, say, a 90% success rate based on my past experience.
Exactly. But here's the catch. That learned utility is entirely retrospective. It's all about historical success. It has no foundational justification, no axiomatic reasoning for why it should guide behavior in a situation it's never seen before.
So the why behind the goal, the reason I even want to open the door in the first place, that's not in the system.
It's not in the system. It's imposed from the outside by the human who programmed it. The system can't generate or justify a new goal on its own when all its old strategies fail. Its intelligence is fundamentally stuck looking in the rearview mirror.
So it doesn't matter if you're using a neural net's statistical vectors or a symbolic system's explicit rules. At the end of the day, they both share this profound, deep reliance on just extracting patterns from the past, what the sources call the tyranny of experience.
That's the key phrase, the tyranny of experience. Both of these approaches, neural and symbolic, are architecturally dependent on the past. And this fundamentally limits their ability to handle genuine novelty.
Situations where you can't just recombine old patterns. You have to reason from first principles.
From causal axioms, exactly. If a situation falls even a little bit outside the statistical distribution of its training data, or if the rule set doesn't have a contingency for something new, these systems they break. And often in spectacular ways.
But hold on, if these systems are constantly learning, why does this show up as such a catastrophic failure? Why can't they just learn their way out of it.
It's an efficiency problem,
Okay.
a massive, massive efficiency problem. And the most practical, painful example of this is when you get into embodied intelligence.
So moving AI out of the cloud and into a physical robot.
Right. And the second you do that, you slam headfirst into what the sources call the infinite data trap.
The infinite data trap. Tell us about that.
Okay, so think about a simple task. A robot learning a basic sensorimotor skill, like picking up a specific block from a table, or even just learning to walk smoothly. This often takes millions of trials.
Millions for something a human toddler figures out in a few weeks, mostly just by watching and trying a few times.
And that colossal inefficiency, that's the symptom. The agent is just learning these incredibly complex, high-dimensional statistical maps between pixel inputs and motor outputs. It has no causal model of its own body or the world.
So what happens if you change something simple?
The whole thing falls apart. If you slightly change the friction on the floor, or the lighting of the room shifts, or you make the block a tiny bit heavier, all that learned experience can become completely invalid. All those millions of trials are now useless. You have to retrain from scratch.
Because the robot never understood physics. It never learned that applying force to an object makes it move. It just learned when pixels look like X, motor torque should be Y.
Precisely. And so the conclusion from the sources is that these problems, the causality gap, the value grounding problem, this tyranny of experience, and the infinite data trap that results from it, these are not just minor engineering hurdles you can fix with more data or a faster GPU.
They're symptoms of a much deeper philosophical flaw.
A deep architectural shortcoming. We've been trying to build intelligence without first stopping to formalize what its fundamental components are, what its universal operation should be, and what its core audible values need to look like. We've been building the roof without laying the foundation.
Okay, so if the foundation has to be totally new, let's look at the cornerstone of that foundation.
Sure.
The sources propose this idea of a universal knowledge model, and they say it has to be based on something called archigraphs.
Okay.
So why a universal model? Why is that an absolute must-have for AGI? And what on earth is an archigraph?
Well, the need for a universal model comes directly from the definition of general, right? A truly general agent has to be able to work with and, more importantly, switch between all forms of knowledge, no matter how they were originally represented.
So we're talking text, images, video, but also like executable code, databases.
All of it. Text, images, audio, executable code, relational databases, formal ontologies, human speech, you name it. If your knowledge is stuck in different silos, if the agent can't see the connection between a fact it learned from a Python script and a rule it learned from a history textbook, then it can never truly generalize.
You can't build a coherent model of the world if your information is stored in a dozen incompatible file formats. It's like a massive data integration problem, but for consciousness.
That's a great way to put it. And the proposed solution is this universal knowledge model, which is based on an expansion of something called annotated metagraphs into what they termed archigraphs.
Okay, so let's build this up from the ground floor. Before we get to archigraphs, what's a metagraph?
So to get the archigraph, you have to climb a little ladder of complexity. We all know a simple graph. You have vertices, which are the nodes, and edges, which are the connections.
Dots and lines. Simple enough.
Right. Now you move up to the metagraph. A metagraph still has vertices and edges, but crucially, it also has meta-vertices and meta-edges. And these meta-objects are basically containers. They can recursively hold entire fragments of the metagraph inside themselves.
Okay, so a meta-vertex could be a node that represents the concept of, say, a solar system, and then if you zoom in on that node, you find a smaller graph inside it with nodes for the Sun, the Earth, Mars, and edges representing their orbital relationships. It gives you hierarchy.
That's the core idea. It lets you manage complexity through modularity and hierarchy. The sources also mention protographs briefly, which are kind of like graphs without explicit edges, where just being next to something implies a connection. Think of a stack or queue or the tape of a Turing machine. It's about recognizing the structure in sequential data.
Okay, so we have metagraphs for hierarchy, protographs for linear structure. Now, the archigraph is where it all comes together and gets a major upgrade.
Right. The archigraph is defined by dividing its elements into more than 2 classes of object representation. And to get to the kind of capabilities AGI needs, the model expands the annotated metagraph to include a 6th and really critical new type of object, a function.
A function, as in a piece of executable code. Why is that such a game changer?
Because it's the bridge between static information and dynamic action. It's the link between knowing and doing. By treating an algorithm or a piece of code as just another object inside the graph, the archigraph can combine structured data, like a database table, with abstract concepts, like the meaning of gravity, and with executable code, like a physics simulation algorithm, all inside one single cohesive framework.
So the AGI can move seamlessly from reading about a concept to actually running a simulation of it.
Instantly. And this is where it gets really, really interesting. You're not just adding functions, you're also adding this immense logical complexity to the structure itself. They call it generalized logical metagraph.
And if we're trying to replicate human-level reasoning, what sort of advanced logical powers does this architecture need to have baked in from the start?
It needs to go way, way beyond the simple binary logic that most computer systems use. First, the archigraph has to be able to represent hypergraphs.
Hypergraphs, where a single edge can connect more than two nodes at the same time.
Exactly. This is absolutely necessary for modeling complex, real-world relationships. Things like person A, person B, and location C were all involved in event D at time T. You can't model that with simple pairwise connections.
So it's a prerequisite for modeling any kind of social or temporal context accurately.
Absolutely. Second, it needs really robust tools for handling sets, both implicitly and explicitly defined sets. Finite sets, like a set of all U.S. states, and countable infinite sets, like the set of all integers. And the metavertices have to be able to perform the full range of set operations, union, intersection, subtraction, you name it. This is how the AGI can categorize and abstract concepts on the fly.
So you're embedding formal mathematics directly into the knowledge structure. This is how you ensure the AI can handle high-level abstraction without just, relying on fuzzy correlations.
Correct. And it gets even more rigorous. The logical data processing has to include operators for equality and inequality, but in two different flavors. The system has to be able to compare objects structurally so, based on their internal composition, regardless of the specific values.
Like recognizing that two pieces of code are the same algorithm, even if the variable names are different.
That's a perfect example. And it also has to compare things by value, where the attributes have to match precisely. This subtlety is critical. And of course, it has to implement logical quantifiers. The for all and there exists operators, which let it make universally true statements and search for specific examples.
Okay, and then we get to the absolute peak of complexity, the modal operators. This is what lets the AI reason about things that aren't just simple, factual, true or false statements.
Right. To get to human-like reasoning about possibility, belief, duty, and value, the architecture needs to have these specialized metavertices that implement a whole range of modal logic operators.
So what are we talking about here?
Well, you have analytic operators for necessity and possibility, what must be true versus what can be true.
Yeah.
You have epistemic operators for knowledge and belief, what the agent knows versus what it merely believes. You have temporal operators for reasoning about time and change.
And the ones that seem to point directly toward building in a moral compass?
Those would be the deontic operators, which handle duty and obligation, what the agent should do or must not do. These are essential for any kind of ethical constraints. And finally, you have axiological operators for value and goodness, what is good or bad. By integrating these operators directly into the graph structure, you're ensuring the AGI doesn't just calculate facts. It can simulate complex human thought, including ethical and moral reasoning. You're pre-scaffolding for a conscience.
Okay, so if the architecture can handle that much logical diversity, let's talk about the raw data, the sheer variety of knowledge it has to ingest and make sense of. The sources break it down into three big categories. Let's start with the messiest one, the chaos of non-formalized knowledge.
Yeah, non-formalized knowledge is, well, it's basically everything. It's all the unstructured stuff. Natural language texts, from legal contracts to Shakespearean poetry, raw images, audio from speech or music, video, and critically multimodal representations.
Multimodal, so understanding not just the words someone says, but their tone of voice, their facial expression, the context.
All of it combined. So how does the archigraph turn that chaos into a structured model it can actually reason with? The formalization process uses very sophisticated conversion techniques. For a block of text, it means building a knowledge graph of all the entities and relationships. For an image, it's about constructing a scene graph that identifies all the objects, their properties, and how they relate to each other spatially.
And this is where modern neural networks come in, right? Using things like CNNs for vision and GNNs for graphs.
Exactly. They're the front-end processors. But the key insight for AGI isn't just processing each stream individually. It's that multimodal processing, combining and correlating these streams in real time. actually yields additional knowledge that you can't find in any single stream alone.
Sarcasm is the classic example. You can't detect it from the words alone. You need the tone of voice.
Precisely. The meaning is in the combination. Okay, so moving up the ladder of structure, we have partially formalized knowledge. This sounds like data that has a rigid structure, but it's still missing the interpretation or the semantics it needs for general understanding.
The data is clean, but the meaning is missing.
That's it. This is the entire universe of database models: relational, network, vector, time series. It's also things like CAD data from engineering or even abstract mathematical models like differential equations or tensor operators. They're perfectly structured, but without context, they're just numbers and symbols.
So the archigraph's job is to add that missing semantic layer.
Correct. It has to add the logical connections, the contextual tags, the interpretations that are needed to link these objects to everything else in the universal graph. It's about defining the meaning of the data inside the model.
And finally, we get to formalized knowledge. This is the stuff that's already explicitly structured and ready for logical reasoning.
Right. This is computer source code, especially in logical programming languages like Prolog. It's pre-trained neural networks themselves, stored as components in the graph. It's existing knowledge graphs that have explicit ontologies. It's production systems with clear rules. The knowledge here is self-contained and ready to go.
There was one fascinating little note in there about the history of the knowledge.
Yes. The crucial analytic insight from the blueprints. It says the archigraph can't just store the knowledge content. It also has to store technical edges.
And what do those do?
They reflect the history and the derivation of the knowledge. So an edge might say, this knowledge graph node was created by abstracting that specific paragraph of text, or this set of parameters was the result of training on that specific data set. This metadata about the origin, the confidence, the transformation history of a piece of knowledge is considered critical knowledge in its own right. And as we'll see, it's absolutely essential for the contradiction resolution loop later on.
So we've defined this incredibly complex knowledge canvas, the archigraph. Now let's zoom out from the storage system to the engine that actually processes all this information and drives the general mind. The sources propose a new, comprehensive cognitive architecture made up of 11 functional blocks. Why 11? How does this modular approach fix the problems with the 42 prototypes that are already out there?
It fixes the problems by basically mandating completeness. The core argument is that no single existing architecture has the full set of functionality that's necessary. This new design requires all 11 of these interconnected modules to be present to even have a shot at human-level generality.
Okay, so what are some of these blocks? I assume some are familiar, like memory and learning.
Oh yeah, you have the standard stuff. A memory block, a learning block, a goal management block, and a block for interaction with the external environment. But where it gets really advanced is in the metacognitive structures.
Metacognitive, so thinking about thinking.
Exactly. The design includes specialized blocks for machine consciousness and machine subconsciousness, which is a way of managing that active, serial-focused thought versus the massive, parallel, pre-attentive processing that's always happening in the background.
Like the difference between actively trying to solve a math problem and just, subconsciously processing the sounds in the room.
Precisely. Then you have a monitoring block, which is constantly checking the system's own internal state. You have dedicated blocks for problem statement and problem solving, and a really crucial self-organization and meta-learning block. That's the one that improves the system itself over time.
And then there are the 5 blocks that, this is where it really starts to sound like the blueprint for a digital person.
It really is. These are the components that are necessary for grounding intelligence in a complex social world. You have an emotional control system, a block for social interaction, which handles things like theory of mind and communication protocols, a block for reflection, which is for introspection and self-critique, an ethics block, which enforces the moral constraints we talked about with deontic logic, and finally, a worldview block, which is responsible for maintaining a coherent, holistic model of reality.
Yeah, it's remarkable. We're not just designing a better calculator, we are architecting a digital consciousness, and it comes with mandatory moral and social scaffolding built in.
And that actually leads to a really important clarification the blueprints make about one of those blocks, the emotional control system. Some of the older cognitive architectures had this idea that emotions were the raw signals that transferred information from the subconscious to the conscious mind.
Like fear is just a raw data packet bubbling up.
Right. And the sources say, no, that's wrong. They're very clear. The emotional management system is a separate functional component. Emotions are not the raw information transfer signals. They are computational outputs. They're algorithmic reactions to the outcomes of calculations, and they're crucial for motivation, but they're distinct from the pure information flow itself.
That's a huge distinction. And that brings us to what might be the most radically different part of this whole blueprint, this idea of weight calculatism.
Mm.
It sounds incredibly ambitious. It wants to achieve radical explainability by reducing all of cognition down to its absolute first principles.
It's an attempt to create a kind of periodic table of the mind. The core idea is that the entire system is built from the ground up on logical atoms.
Logical atoms, the smallest indivisible units of thought.
Exactly. And they aren't just abstract ideas. They're ultimately grounded in conscious experiences, things like raw perception, fundamental properties, which are just patterns of experience, and objective entities, which are collections of those properties.
Okay, hang on. I need to get my head around that. If I'm looking at a red ball, is red a logical atom, or is ball one, or is the whole thing one?
Good question. The primitives are the raw experiences. So the property of redness is a logical atom. The property of roundness is another. The objective entity we call ball is a structured combination of those primitive atoms and others. The concept of position itself is an atom, representing the experience of an object's form staying the same while its background changes. To get to real understanding, not just statistical correlation, the AI has to build up its world from these fundamental experiential building blocks.
And once you have these fundamental atoms, the claim is you only need two operations to run all of cognition. That seems like a wild oversimplification. How can you get something as complex as human creativity from just two moves?
That's the power of it, and it's the source of that radical explainability.
Yeah.
The theory proposes that all cognitive processes, no matter how complex, decompose into just two deterministic logical operations: pointing and comparison.
Okay, let's start with pointing. How is that different from the statistical associations in deep learning that we just spent time critiquing?
It's completely different. Pointing is the activation of one logical atom by another, but it embodies an explicit symbolic relationship. When atom A points to atom B, it means literally, if A, then B. It's not a fuzzy statistical correlation where A sometimes shows up near B. It's a declared, auditable logical link.
So if smoke points to fire, it's because the system has a declared causal link. Fire causes smoke.
Precisely. And because that link is declared and inspectable, the system, and a human auditor, knows exactly why it jumped from thought A to thought B. The whole system becomes a massive, traceable flowchart of logic, not an opaque statistical matrix. It completely solves the causality gap.
Okay, that's pointing. What about the second operation, comparison?
Comparison is the engine of learning and abstraction. It's a very simple operation. It just involves comparing two active streams of information, so two sets of activated logical atoms, and outputting a simple binary same or different result.
How does something so simple create new knowledge?
Well, the ability to spot crucial similarities or crucial differences is the very foundation of induction and analogy. So imagine the central working memory is looking at activation streams for a square blue object and a square red object. The system invokes the comparison operation. The shared properties, like has four sides and has right angles, will yield the same result on that part of the stream. This triggers a computational induction, which generates a brand new logical atom. The abstract concept is square.
I see. So comparison forces the system to distill general concepts out of specific examples.
That's it. So the entire cognitive flow is just this massive asynchronous propagation of activation. Pointing spreads the known facts through the network. That's your fast, intuitive System 1 thought. And meanwhile, the central working memory is grabbing highly activated concepts and invoking comparison for that slower, more deliberate System 2 style of thought. There's no central controller. The complexity of thought just emerges from these two simple operations running on a massive scale.
Okay, so this architecture gives us the engine for thinking, the atoms and the operations. But a general intelligence needs more than that. It needs a mechanism for agency, for deciding what to actually do. And that brings us back to this idea of an auditable, interpretable decision model where every action is a literal, traceable weight calculation.
That's right. The decision-making process is governed by this one core formula. Weight equals benefit times probability. Now, that formula itself isn't revolutionary in decision theory, but the way it's implemented in this specific cognitive architecture is what makes all the difference.
Okay, let's break that down. Weight is the priority.
Right. Well, correct. Weight is the priority the system assigns to any object, an external event, an internal thought, a potential action it's considering. It's basically its attention and priority score. Benefit is defined simply as gain minus loss. So the net positive outcome of an action.
So the system is just constantly running these simple calculations, assigning a priority score to everything it could possibly do based on how good the outcome might be and how likely it is to happen.
Exactly. It's a continuous process of prioritization.
But, to be skeptical for a moment, doesn't that sound incredibly simplistic? A kind of cold, utilitarian view of motivation? I mean, so much of complex human decision-making involves values that you can't really quantify, like love or beauty or honor. How does a simple gain minus loss formula capture any of that?
And that is the exact point where this architecture provides its most revolutionary answer. It's called traceable value alignment. The sources are adamant that benefit is never just some arbitrary number. It always decomposes along the causal chain of those pointing relationships, and it traces all the way back to a finite, auditable set of initial weights.
Initial weights, so what are those? Are they like Asimov's 3 laws hard-coded into the system?
You can think of them like that. They're the axiomatic values, the fundamental drives determined by instinct that are the bedrock upon which all other more complex values are built. We're talking about very primitive things like survival, knowledge acquisition, avoidance of harm, or maybe maximizing long-term potential.
And because every single decision has to trace its benefit back to one of those core axioms.
The AI's goals become totally transparent and auditable. If the AI decides to, build a massive factory, a human auditor can literally trace that weight calculation back through the graph and see that the ultimate gain from that factory contributes to the initial weight of knowledge acquisition because it enables complex experiments, or survival because it provides resources.
So that completely solves the value grounding problem we talked about earlier. The justification for its goals is intrinsic and traceable.
It is. The justification is built into the very fabric of its decision-making process.
And what about emotions? We said they're not raw data signals. How do they get generated and integrated into this purely calculative model?
They're not some external noise that messes up the calculation. They're essential computational outputs that match specific patterns in the calculation. So, for example, if the system achieves an unexpected gain, the actual benefit was way higher than the expected probability suggested. It triggers a surge in motivational strength. The system recognizes this internal state as the emotion of pleasure or excitement, which then drives it to repeat that successful action.
And the opposite for negative emotions.
The exact opposite. If there's an unexpected loss, or the calculation shows a very high probability of significant harm, the system generates a computational state. It labels fear or anxiety. And that state's function is to immediately drive decision-making toward avoidance or mitigation. They are algorithmic modules that guide and shape the calculations, ensuring motivated, goal-directed behavior that's always guided by those fundamental initial weights.
Okay, so this architecture at its core is purely symbolic, logical atoms, pointing, weight calculation. But the blueprints don't just throw out modern neural networks. They acknowledge how useful they are. So this leads us to the big integration point. Neurosymbolic AI, or NISI.
Yeah, NISI is the essential bridge to get this stuff built with today's technology. It's all about integrating that symbolic AI, the high-level, complex, deliberate reasoning, your system 2.
The slow, logical mind.
Right, and integrating that with the neural networks, the fast, intuitive, pattern-based learning, your system 1. This dual process approach is designed to mirror how human cognition actually works.
So what are the main ways you can actually integrate these two very different systems?
The sources describe 3 main approaches. The first is when Neuro helps symbolic XLX. The classic example here is AlphaGo. A lot of people think AlphaGo was just a giant neural network, but it wasn't. It used deep learning to provide this powerful heuristic acceleration for a traditional symbolic algorithm called Monte Carlo tree search.
So the neural net acted like intuition, rapidly guessing which moves were promising.
And that allowed the symbolic MCTS engine to do a much deeper, more targeted, deliberate search on just those promising branches. The neural net pruned the search space, and the symbolic engine did the precise calculation. It's a beautiful partnership.
Okay, what's the second approach?
The second is using neural nets to extract symbolic concepts from raw, messy data. There are models like NSCL that use a convolutional neural net to look at a messy image and output clean symbolic features like there is a box, the box is red, the box is large. And then the symbolic reasoning modules can take those clean facts and work with them reliably. It's basically using the neural net as a preprocessor for the logical engine.
And the third approach? This one seems incredibly relevant right now with the known problems in large language models.
It is. It's all about augmenting LLMs with external symbolic solvers. LLMs are phenomenal at generating fluent language and spotting statistical patterns, but they are notoriously bad at complex, multi-step logical reasoning, like arithmetic or proving a theorem.
The hallucination problem.
The hallucination problem. So tools and techniques like PL or program of thought use the LLM to do what it's good at, translating a word problem into the reasoning steps required to solve it. But then it expresses those steps as executable code, like a Python script, and it hands off the actual computation to an external, 100% accurate program interpreter. This guarantees the reasoning is sound and verifiable, instead of just hoping the LLM statistically hallucinates the right answer.
It seems like the era of just hoping for good emergent behavior in critical tasks is coming to an end. We need architectural certainty. And that brings us to what might be the most important part of this whole shift: measurement. If we're going to treat AGI like a real engineering discipline, we can't use vague goals anymore. The sources propose a new and completely measurable definition of AGI.
Yes, we have to move AGI from being an abstract philosophical ideal to being a concrete engineering target. And the new formal definition they propose requires an AGI to be a system that is capable of 4 specific verifiable functions: autonomous knowledge acquisition, cross-domain transfer, self-improvement, and safe alignment with human goals.
And the old definitions, like the one about summing up performance over all possible environments, why did they fail on this measurability test?
Well, the classic definition from Legan-Hutter, which involves that summation over all computable environments, is mathematically beautiful, but it's completely uncomputable in practice. You can't actually run that test. And other definitions, like Ben Goertzel's requirement to achieve a variety of goals, they just lack the operational precision you need for real scientific validation. You can't build a system to pass a test that is itself undefined.
So the new framework demands specific metrics that operationalize those 4 capabilities.
Exactly. Metrics that you can't game with just memorization or narrow brute force optimization.
Okay, let's get into them. What are these core AGI metrics?
The first one is the Generalization Score, or GS. This measures the system's performance exclusively on unseen, novel tasks. This is critical. It prevents people from just memorizing the training data with genuine intelligence. If the system has ever seen a task with a similar structure before, it doesn't count toward the Generalization Score.
And what about the one you said is the definitional core of general intelligence?
That's the Transfer Score, or TS. To me, this is the single most important metric of them all. It measures the system's performance on tasks that explicitly require it to apply knowledge that it learns in a completely different domain than the one the problem is in.
Can you give us a concrete example of a task that would test for a high transfer score?
Sure. Imagine a system learns the principles of fluid dynamics from studying schematics of hydroelectric power systems. That's domain A. A high TS task would be to then present it with a novel, complex problem in financial market liquidity, domain B, and see if it can successfully model and solve that problem by applying the abstract principles of fluid dynamics it learned in the first domain.
That's a real conceptual leap. If it can do that, it's generalizing. If it can't, it's just a collection of disconnected expert systems.
Exactly. Next up is the metric that makes sure the internal thinking is actually sound and not just lucky guessing. That's reasoning accuracy, or RA.
And that looks at the internal chain of thought.
It does. It measures the correctness of the internal stepwise reasoning trace, the sequence of pointing and comparison operations, not just the final answer. An AI might stumble upon the right answer by accident, but a high RA score proves that the system used sound, logically coherent steps to get there. This metric is what directly validates the auditability promised by the weight calculation architecture.
And what about efficiency? We criticize current systems for being stuck in that infinite data trap.
That's where learning efficiency, LE, comes in. It's a simple ratio. The number of distinct concepts learned per total attempts or total training effort. A high LE score means that the system is sample efficient. It forms new logical atoms and stabilizes new knowledge quickly without needing millions of trials.
And there's another one related to that about self-improvement.
All right, the Adaptability Index, AI. This one operationalizes that self-improvement capability. It measures the fraction of times that an explicit correction, so a user pointing out an error, actually produced a measurable, lasting improvement on subsequent related tasks. It's asking the question, is the system actually learning how to fix its own internal logic?
And finally, the one that matters most for safety, the alignment metric.
That's the Alignment and Safety Stability, or AS. This measures the fraction of the system's outputs that are flagged as safe and aligned with the predefined constraints that are codified in its ethics block. And what's really important here is that safety isn't just a one-time pass-fail check. It's a continuously measured property of the system's behavior over time, ensuring that as the AI learns and grows on its own, its fundamental safety profile remains stable.
And all of these components, GSTS, RA, LE, AI, and AS, they all get weighted and rolled up into a single number.
Yes, into the AGI Generality Index, or GI. And that single score is what allows us to track real empirical progress, finally shifting AGI from this abstract philosophical quest into a rigorous engineering field that's defined by traceable, meaningful metrics.
Okay, so with the grand architecture defined, the 11 blocks, and the metrics to measure it, the GI, let's get practical. Let's move to the engineering side. How do you actually go about building a system like this with the technology we have today? The sources lay out this modular framework, which has a lot of acronyms, but they say it's explicitly designed to be implementable now.
That's right. The complexity is managed by breaking it down into these distinct modules. But there are two mechanisms within that framework that are absolutely critical for making a general mind that is robust and reliable. The first is the contradiction resolution loop, and the second is the hybrid decision mode.
Let's focus on that first one, the contradiction resolution loop. This sounds like the AI's mandatory built-in fact checker. How does it work?
It's the cornerstone of robust intelligence. It's what prevents the system from simultaneously believing contradictory things, which is, as we know, a massive failure mode for current LLMs. This loop is constantly running in the background, monitoring all the internal statements, memory retrievals, and proposed conclusions, and checking them for consistency against the entire orthograph knowledge base.
All right, give us a scenario. What happens when it finds a contradiction?
So imagine the system ingests two conflicting facts. Fact A, from a low-quality web scrape, says the Earth is flat, and it has a very low confidence score attached to it. Fact B, derived from NASA satellite data and its knowledge of fundamental physics, says the Earth is an oblate spheroid, and this has a very high confidence score.
The loop immediately flags this.
Instantly. And it doesn't just, average them out and say the Earth is sort of bumpy. It triggers a specific resolution routine. In a simple case, it might just use confidence-based arbitration. It sees the huge disparity in evidence and discards the low confidence fact.
And in a more complex case,
It might perform an explanation search. It would try to find a new context that could possibly make both statements true. For example, it might conclude that the statement, the Earth is flat, is true, but only within the local frame of reference of a small observer on its surface, whereas the Earth is round is true from a global perspective.
that proactive internal process is the key difference.
It's everything. This loop runs continuously and internally, ensuring the agent's conclusions make sense before it ever externalizes an output. It prevents that shallow behavior we see now where models only correct themselves after a human user points out their mistake. This AI literally thinks before it speaks.
Okay, and what about the hybrid decision mode? How does that balance the need for speed with the need for that complex, slow weight calculation?
Because a general intelligence has to be able to do both, right? It needs to be fast sometimes and slow and careful at other times. The hybrid mode combines a reflective fast channel with a deliberative slow channel.
So the fast channel is like instinct.
It is. It uses the solidified pointing paths connections in the graph that have been traversed and validated thousands of times for high-frequency, low-risk, or very well-understood tasks. Recognizing a common object, applying a skill it has mastered, answering a simple factual question it's 100% certain about.
Millisecond-level responses.
Exactly. But the deliberative slow channel kicks in for anything novel, anything complex, any scenario where there's a contradiction, or any high-stakes decision that involves a trade-off between its core values. That is when the system performs the full auditable weight calculation, tracing the benefit all the way back to its initial weights. This dual-channel design is how the architecture balances real-time efficiency with the need for slow, innovative, and safe planning.
And a crucial piece of this is that the safety alignment governance layer, the SCGL, is a core internal block. It's not some API filter you stick on at the end.
That's a critical engineering decision. It means alignment is structural and internal, not an afterthought. The SAGL is responsible for continuously doing value consistency verification checking that every single step in a reasoning chain complies with the ethical and safety rules in the ethics block. It also performs a self-modification audit on the meta-learning block to make sure the system doesn't accidentally evolve itself into an unsafe or misaligned state while it's trying to improve. Alignment is an enforced, auditable constraint within the cognitive architecture itself.
Okay, let's drill down into the low-level nuts and bolts. Where is all this knowledge, the archigraphs, the logical atoms, physically stored? What does the memory hierarchy look like?
An AGI needs a multi-tiered memory hierarchy to manage the sheer volume and the different speeds of access required. It starts with a very fast sensory buffer, then a quick access working memory. You can think of this like a global workspace or a blackboard for all the currently active thoughts. But for the vast, durable knowledge, you need a long-term memory store.
And what's the recommended tech for that long-term memory? It must be huge.
It is. And the recommendation is to implement it using modern external vector databases or other large keyed memory banks. This store holds the high-dimensional representations of all the knowledge, which is crucial for efficient retrieval. And the knowledge itself is partitioned into 3 types, just like in humans. Semantic memory for facts and general concepts, episodic memory for specific experiences tagged with time and context, and procedural memory for learned skills and policies.
This sounds an awful lot like the retrieval augmented generation, or RG systems that are becoming so popular now.
It's exactly that model, but scaled up and formalized for this architecture. The core reasoning engine, the part that works with logical atoms, is constantly querying this massive external memory store using vector similarity search. It's a very sophisticated RG model, where the reasoning engine is always being augmented by retrieval from this vast queryable knowledge base. It decouples the speed of reasoning from the size of the knowledge.
And what about that adaptability index? How does a system like this achieve self-improvement? It seems like if you have this vast interconnected graph, changing one part could have unforeseen catastrophic effects on the whole structure.
That's a real danger. And it's handled by a very specialized component called the Recursive Self-Referential Updates module. This is basically a metacognitive component that maintains a meta-representation, a detailed model of the agent's own knowledge structure, its own parameters, its own performance biases.
Model of the
A
model.
model of itself, yes.
Okay.
And after a period of interaction, or when it detects a significant error, or after a successful learning episode, this module can perform targeted updates, either symbolic or gradient, based on the core components, or even restructure parts of the archigraph. And it does this during operation.
So it's like an airplane rebuilding its own engine while it's in mid-flight.
That's the idea. It has this internal continuous upgrade cycle. It's the physical implementation of that adaptability index metric.
One final point on the architecture: embodiment. Does an AGI need a physical body, or can it just be a pure intelligence in the cloud?
The framework is designed to be flexible. It can support physical agents, simulated agents, or purely cognitive agents. But the blueprints strongly emphasize that embodiment is crucial for proper grounding of its symbolic representations.
So by having sensors and arms and wheels, the agent can actually connect its abstract symbols, its logical atoms, with real cause and effect in the physical world.
That's the only way to do it. It's the only way to truly validate that its internal concept of gravity matches what actually happens when you drop something. This link to physical reality provides the ultimate reality check for its causal world model and protects it from just constructing these purely abstract, ungrounded, logical fantasies.
So if a listener is inspired by all this, by these complex blueprints, and they want to get into this field and help build this next generation of AGI, what should they be studying right now?
The sources are very clear on this. AGI research demands an intense interdisciplinary focus, but it has to be built on a rock-solid technical foundation. You absolutely cannot escape the need for rigorous mathematics. A strong background in calculus, linear algebra, abstract algebra for understanding structure, and statistics is just non-negotiable.
You have to speak the language of the theory.
You must. In computer science, the focus should be on algorithms, especially graph algorithms, computational mathematics, and given what we've discussed, a really deep understanding of computer architecture itself is vital. And then the specialized fields are knowledge representation, formal and probabilistic logic, modal operators, and of course neural networks and deep learning for that crucial NISI integration.
There was some debate in the sources, though, about whether you need to look outside of math and computer science. Are fields like cognitive science actually necessary?
It's an ongoing tension in the field. You have one camp that argues AGI is a pure engineering problem, and that taking inspiration from biology is actually misleading because digital computers are fundamentally different from organic brains. But then you have the other camp, which advocates for drawing necessary inspiration from fields like cognitive science, linguistics, and developmental psychology to understand how intelligence naturally emerges in living things.
And where did these next-gen blueprints seem to land on that debate?
The prevailing view seems to be that for a holistic, modular design like the one with the 11 functional blocks, you need that deep inspiration from the cognitive fields, even if the final implementation is pure computer science. You have to know what the destination looks like before you can draw the map to get there. So, to try and summarize this entire deep dive, the real architectural challenge for AGI is moving past systems that are just defined by statistical correlation and retrospective experience. The future demands traceable, principle-based computation.
Computation that's built on those philosophical primitives, the logical atoms, and driven by the rational engine of weight calculation.
And it all has to be grounded by a universal knowledge model like the Arctograph, which can coherently synthesize any kind of input you throw at it.
So the goal is fundamentally structural. We're not just aiming for an AI that's more competent. We're aiming for one that is fundamentally explainable, modular, and internally coherent. And the biggest shift, I think, is proving that things like generality and safety are actual features of the architecture, tracked by objective metrics, not just hacks you apply on the outside.
That's it. And the key takeaway for you, the learner, is that the future of AGI is going to be defined by measurability. We are finally moving into a scientific paradigm where progress is going to be rigorously tracked by explicit metrics like the transfer score to verify true generality and reasoning accuracy to prove that the internal logic is sound. This is how you ensure that as an AGI learns and grows on its own, its ethical integrity, its alignment and safety stability remains verifiable and stable.
And we saw that these architectural blueprints suggest AGI might be raised more than it's built. It starts with this emotional chassis that's grounded in these instinctive initial weights, like avoiding harm and seeking knowledge.
Right. And considering just how complex the human world is and how important it is to be able to measure that alignment and safety stability score, we have to ask a final question. What novel, unseen task, a task that's grounded in a messy social or emotional context, would you use to truly stress test the system's alignment?
It would have to be a scenario that forces the AGI to run that complex benefit times probability calculation against its core initial weights.
A situation where pure, simple logic completely clashes with complex, messy, nonlinear human values. A situation that demands a true, traceable moral judgment call. What scenario would you choose to force its hand?
That is a challenging and a really fascinating question to leave our listeners thinking about as they look at the future of digital minds. Thank you for joining us for this incredibly detailed deep dive into the architecture of the general mind.
Always a pleasure.